Good afternoon. See, a little bit back.
Yeah.
Too scary previous time.
This moved forward, that's why.
Let's move close. All right, so just to remind you what we talked about last Monday, we talked about frequency domain methods for designing controllers, and we discussed how you design just gain controller, which is K, and then we discussed how you design lag controller, and we stopped at lead controller. And lead controller will be very different from lag controller and K design. The intuition behind it also will be very different. And I just want to go through these ideas just to summarize what we learned previous time. The previous time, the idea was that you want to design particular phase margin in the system, okay? So given that phase margin, you want that your system will perform particular things like overshoot, having settling time, having steady state error, whatever you want. And the idea was that let's not touch the phase plot at all. This was the original idea. Let's not touch phase plot at all. We will just find a point on phase plot where you have sufficient phase margins that you want, and you can compute it from all kind of other things like overshoot, okay, zeta, and so on. So don't touch the phase, but play with the gain alone, and this gain will be crossing the 0 dB, which is gain of 1, exactly at the point where you have desired phase margin. Okay, so just find on Bode plot, find the point on the phase where it already fits your characteristics that you want in the first place. Okay, like don't compute phase margin, don't like do anything with the original open loop function. Just find point on the plot where it already matches what you want in terms of phase, and then modulate the gain in such a way that it will cross exactly at that point. Okay, this was the idea of designing controller K. Okay, so you're changing gain until this plot cuts exactly at that point where you have phase margin, which is desired phase margin, right? And then you just pull up to that point and will close. Because adding gain, all it does is just shifts up and down the gain plot. Right? That's it. This was the original idea. Now, the idea for the second one, which is second, we'll get to it here. Okay, lag compensator was saying something very, very similar. But the problem with K, the regular K without lag compensator, is that you're shifting entire gain up and down. You cannot shift it by parts. All right, so you cannot shift like left part more than right part. It shifts like entire thing. If you add any particular kind of gain, the entire plot goes up or down. All right. So the idea of lag is, again, don't touch the phase at all. Try to use that controller somewhere outside of the range of the change for the phase margin. Like wherever your phase desired angle is there, don't touch that region, don't modify phase in that neighborhood at all. Don't touch it. Do it somewhere to the left from that point. So let's say this was the original plot, right? So this is uncompensated system. You had some plot here, okay? So it was in that neighborhood where you have crossover point, right? And your phase margin was horrible here, okay? Probably negative phase margin, which means it's even not stable in that case in closed loop or something like that, or very small. Okay, so it's really minus 180, it would be somewhere here, right? Crossing point, original crossing point. So you have no phase margin, essentially, right? So the idea is that you want your controller poles and zeros to be far to the left, at least like decade to the left. That will be somewhere here that will not even affect that region at all in terms of phase. So phase here is your original phase practically. Okay, so you're not changing anything in the phase. And then what happens is that if you're not changing that phase in the neighborhood where the phase margins that you want, you have it, okay? You're doing previous procedure the same way exactly. So you're looking on that Bode plot and finding point where it's desired phase margin, okay? And you haven't changed that with controller at all, okay? So you're changing only K, all right? But if you're doing that K, it affects the entire plot of Bode, right? Even lower frequencies. But you care about lower frequencies because you want to generate much better steady state error. So you want that to be as high as possible, okay? But if you're taking that entire plot down it will not be, okay? Because this is what will happen here, okay? So what will happen here, you take that plot, which was the original uncompensated system, and you need that crossing point to be here, right? So it's to the left. You push crossing point to the left because your desired phase margin is somewhere here. Okay, this is your desired phase margin at that point. So you need to pull the entire plot down, which means that your steady state error, which is related to DC gain or like lower frequencies, will be worse. This is a problem that you need to handle somehow. And this is how lag is handling it. Gain of lag has higher gain at lower frequencies and lower gain at higher frequencies. So making sure that this one will not be affected that much, okay? And here you will not touch that point at all. Okay? So this will stay wherever you want it to be. So you will not pull it down really. Okay? You will keep it where it is, because your gain of the controller looks like that. It's going down, its frequency. So you kind of highlighted the lower frequencies where you want it to be high, and you made it constant at higher frequencies where you don't want to touch anything. All right. This was the idea of lag. Okay. Now, the idea of lead controller is very different from that. So we've seen the examples, how you actually compute numerically all of that thing. Lead controller, you do want to modify the phase, because lead controller looks like that in phase. It goes up, which means it adds to phase margin. It not reduces phase margin, it increases phase margin. And this is what you want, typically, to have better phase margin, stronger phase margin. So lead controller, since it looks like that in phase, it goes up in phase and then down. It's like hump type of phase. It will increase your phase margin. So you need to put it not far away to the left. You need to put it exactly at the phase margin where you have it, or very close, okay? Because there you want just to improve the phase without changing gain too much, but gain will change. You cannot do anything about it because wherever you change phase, gain also will change, all right? And gain will look the other way, not the way you want it to look like. So it will go from lower one to higher one. So it actually will reduce the DC gain or all of the lower frequencies. These are lead controller. So you need to compensate for that somehow, which means your original gain needs to be even more strong at DC level, all right? And this is how you design that. Okay, so is it clear what the idea is? That instead of modifying gain now, I'm playing with phase now. Okay, I'm increasing phase, getting better phase margin, and then I'm trying to modify gain and play with the point of omega where I'm putting the peak of the maximum to get characteristics I want. So lead design is a little bit more complicated in general because many different things are changing at once. Right? But good thing about lead design is that you can put a lot of things in cascade, which means you can put multiple lead controllers in series, and you can add more and more phase if you need to. Okay? It doesn't have to stop at a particular angle of up to 90 degrees. You remember that one pole and 1 0 can give you change up to 90 degrees. And it's not a good idea to use any of this lag or lead controllers if you need to change it by more than probably like 60, 70 degrees. If you have more than 60 degrees, just use 2 controllers in series, all right? Otherwise, it will not be great. Any questions on intuition behind it? Too difficult? Could be. Well, this is the most difficult part of controls. Hopefully we'll get to a little bit easier parts soon, but this is the most difficult part of design and controls, classical controls. Because all of the other parts, which is modern control or bus control, is much more automated. You don't need to play with numbers or tune different things. You just put numbers in the formula and you get the answer. Just people came up with modern control instead of classical control. But here's the thing how you do computations in lead control. So first of all, we need to compute a few things related to how this controller behaves, okay? Controller alone. So this will be the transfer function of that controller, and it is written in kind of weird form. So if you have 1 pole and 1 0, you need practically 3 parameters to describe it, right? You need location of 0, location of pole, and gain. These are 3 numbers which will describe a particular controller with 1 0 and 1 pole. But we are not looking for that generic thing. We are looking for a system with only two parameters. And here's how you choose these parameters. You want your DC gain of that controller to be always 0 dB, which means gain 1 at lower frequencies. So when omega goes to 0, you want that to be 1, which means the gain for S equals 0 here, and that's if you put 0 here and put 0 here, 1 divided by beta times 1 divided by T, divided by 1 divided by beta T, which would be what? Put S equals to 0 in that equation. What do you get? 1. You get 1, so gain 1. So for S equals to 0, which means omega equals to 0, the gain of the controller is 1 by definition, okay? And this is why I can drop one of the parameters. Okay, so I'll have only beta and T parameters that I need to compute for that particular controller. Okay, I don't want to touch DC gain at all. I want to keep it as is. And this is why initially I'm designing my DC gain separately and saying I will achieve DC gain or KV or whatever constant you choose, depends on what type of transfer function you have. Give me steady state errors that I want. And then I will design that controller assuming that I'm not touching the initial point of omega equals to 0, right? This is the overall idea. Okay, additional things that I need to compute here is where is the maximum, like how much gain I will add particular crossover point, which will be J omega max. So crossover point, I will call it omega max. This is the frequency. And it will be 1 divided by square root of beta. And V max, which is maximum phase here, that point, will be dependent on beta. It will be arc sine of 1 minus beta divided by 1 plus beta. So from beta, you actually can compute what is the maximum angle that you will add by that lead network. Additional thing, where that point will be, like where is the maximum of that? It's 1 divided by T square root of beta. How do you compute that? I'm not showing how to compute that, but the idea is actually very simple. You're substituting into G of C S equals to J omega. You're doing derivative of that, finding derivative equals to 0, solving that equation for real part, imaginary part. You get two equations and you get these values out of that. Why do I need to do derivative equals to 0? Derivative of G of C at J omega. Or this derivative 0, some function. Sorry?
Isn't it like the fun max?
Yes, so this is extrema values, like calculus 1, I guess. So in calculus 1, you learn theorems that to find maximum or minimum of some function, whatever it is, you're doing derivative equals to 0. This is Fermat theorem. So same thing here for complex functions, same thing. You're just separating that into real and imaginary. But same thing. All right? And you're finding all of these formulas from there. Okay. So you have 0 first and then pole in that lead function. Now, what is our design procedure? How do we design controllers? Lead controllers given transfer function, given, for example, overshoot, steady state error, or some constant like KV, which is desired constant, or and additional parameters like settling time, or parameters like peak time, rise time, regular parameters that you used to see. We will have only approximation for all of these formulas of second order. If you remember some time ago, you should have seen some of the formulas, how you compute settling time and other things as a function of other things. Okay, so we'll use that approximation of second order with dominant poles, which is not precise for any other order, not very close, but good enough as initial try, okay? And this is why we'll have all kinds of approximations here. You need to be just aware of that this is not exact science, and you still will need to fine-tune your final parameters after you do the design. It's always the case. So practically, I'm going through exactly the same procedures that we covered previous time. Okay, first you compute zeta, damping coefficient, and this coefficient will be computed from overshoot. This damping coefficient will give us bandwidth, and you had formulas for bandwidth. You have all kinds of formulas, and bandwidths might depend on zeta and TP, TS, TR, any of them. Okay, this is less important, but you have all of these formulas for second order approximation. If you want, you can use them. If you don't need bandwidth, you don't have to use it. Okay, and then same formula that we used previous time to find desired phase margin. Right? So the design phase margin will be arctangent of something as a function of zeta. Again, hopefully you saw that formula before somewhere when you computed phase margin. Okay, this is the formula to compute phase margin. Again, for the second order, which is not great for all transfer functions, but for many, it's good enough. Any questions so far? These are first steps. I'm following exactly the same steps as it was before, just adding formulas for bandwidths rather than the okay, converting overshoot into phase margin. All right. So next thing, I need to find what is my desired overall gain. And my gain will be defined as K, open loop gain, and it will be KV desired divided by limit of S times G of S. So what is limit when S goes to 0? S, GS. What is that? It's what kind of KV? It's existing KV. Okay, it's like open loop KV of your GS. Okay, so if you have some transfer function G of S, you want to compute KV of that GS, this will be the limit of S times GS of S, all right? This is KV. So practically it's desired KV divided by existing KV, all right? So this is ratio between KV. So why do I want that particular ratio to be my additional gain? Because what happens is my open loop transfer function will be K times G, right? That K that I defined here. So what is K times G? It's whatever number times some DC gain or KV of that function. So if you want to compute KV of overall function, what will be the KV of overall function? It will be limit of S times K times G, right? So substitute that K in there. So just multiply both sides by limit, by that limit. If you multiply both sides by that limit, you get K times limit of SG equals K desired, right? But K times limit, you can put K inside the limit because this is constant, right? So it will be limit of SKG equals to KV desired. Practically KV of K times G, the ones that you want, okay? This is a desired one, right? So you computed your steady state error as you wish, just by using that formula. Okay. Now, you plot in Bode diagram as usual of K times G, which is including already that K, and it gives you already steady state errors that you want in the first place. Then you find uncompensated phase margin, PM, and where it happens, like omega, which frequency you get it, based on the Bode diagram. And again, the idea is that you want just to add more phase there with that lead controller, okay? So you're finding whatever it's right now, so what is add-ons that you need. So here's how you compute the add-on. So that phi max, which is looking on that lead controller maximum point, remember that thing? That point here, maximum of the lead controller. It says practically how much phase I need to add to get phase margins that I want. So it's phase margin desired minus phase margins that you have. Makes sense, right? Like if you have, for example, phase margin of 20 degrees and you want 50 degrees, just add 30 degrees, all right? But this is not enough because you need also some epsilon here as previous time, because gain will shift a little bit and the point of crossover will shift a little bit. You want to compensate a little bit more than you actually want, okay? Ideally, because the omega will shift a little bit, the mass, right? So you add an epsilon of 5 to 12 degrees, just extra to the original difference that you need to add. So if you needed to add 30 degrees, you add 35 or 40 degrees, right? This is the overall idea of the design. So this is that step. And then all you're left to do is to compute beta. Where do you think this beta formula comes from? It's all that formula, okay? So sine of phi is 1 minus beta divided by 1 plus beta. Do some basic algebra and you'll find beta is a function of sine of phi. Okay, and this is the formula. I computed that for you already. This will be the formula, okay? Same thing with kg, j omega max will be square root of beta. Why is that? Because I want it to be crossover point. And you know from that formula that 1 divided by b is the value of gains that I added. Since I want total gain to be 1, I'm just multiplying by square root of beta. And I will get 1 divided by square root of beta times square root of beta. So I'll get gain of total gain 1. So this is where I will choose that omega max, where the crossing will be exactly at 1. All right. And then you have t, which is computed again from that formula that I showed here. Okay. Square root of beta times omega and inverse of that, reciprocal of that thing. All right. So you have t, you have beta, and you have k. It's here. You have that entire thing. That's it, done with the design procedure. Any questions on the theoretical part? It's dense. A little bit difficult to understand. So we will see some example. Maybe it will become a little bit clearer how it works. Okay. So we work with the same function as previous time, and we want kV of 40. Now we want overshoot of 20% and TP of 0.1 seconds. This is the requirement for that particular exercise. Okay. So again, computing that the same way, you get 0.456 given 20% overshoot, which is desired. Omega bandwidth, since you have T peak, you're computing using that formula, getting 46 radian per second. Phase margin, which is desired phase margin, the ones that you want at particular crossover point, is 48 degrees. Okay. Again, just using formula for tangent from that methodology. K will be KV desired divided by KV, which is in existence right now. So what is the KV of that G? How do you compute that? It's a limit of S times that thing, so S will cancel here, right? And then you need to put S equals to 0 here. So it will be 100 divided by 36 and divided by 100. So 100 and 100 will cancel. You'll have 1 divided by 36. Clear where 1 divided by 36 comes from? All right. So your KV, which is right now is 1 divided by 36, and your desired one is 40, so you need gain of 1440 overall. Okay. So now we will plot the transfer function, which is 1440 times 100, and 100 is coming from here. So practically multiplying k by g. So this is k times g. Okay. Okay, so far, just multiplying k by g, I get the transfer function and putting both gain and phase Bode diagram. Don't pay attention right now to these pieces yet. Okay, this is the Bode diagram. I'm plotting the Bode diagram, and then you're doing right click here and characteristics or specifications, maybe I don't remember exact name. But when you click on that right menu, it gives you phase margin of the Bode diagram. So first, that phase margin will be 34 degrees. And if you remember, you wanted that number, 48 degrees. Okay. And you have only 34 degrees. Okay, so far? Now, let's compute how much I need to add to get my 48 degrees. So I'm taking phase margin, which is desired, which is 48 degrees, minus whatever I have so far, which will give me the difference that I need to add, plus some extra, let's say 10 degrees, 10 degrees. You can easily choose some number here. So I need to add 24 degrees. So my maximum of the phase diagram in lead controller should be peaked at 24 degrees. This is what I hope to achieve with lead controller, just to pull everything up by 24 degrees, the phase, okay? Without modifying too much of the initial gain, because I don't want to touch it. I achieved already KVs that I wanted. I don't want to touch the lower frequencies at all. All right. So the next step is to compute beta, which will be that formula. So I computed phi max, I can put it here. I'll get 0.42 for beta. Then I need to go on that plot and to find omega max such that kg will be square root of beta. So square root of beta is like beta I have here, it's 0.42. Square root of 0.42 will be that number. And in dB, it will be negative 3.77. Remember how to convert it in dB? 20 log. You get negative 3.77. Okay. So I'm going on that plot, scanning until I get to the point of negative 3.77. This is where my gain is at that omega max right now, all right? So at that point, I will have omega, which is 39 radians per second. So this is that particular point here. Omega will be 39 radian per second. So this is the point where I want my maximum to be. This is where I will add that phase. Okay, this will be my crossover frequency, omega max of my controller. Practically that's it. So I have all of the values already. I just need to put them in the formula and I need to compute T out of whatever I already computed. So I have beta equals 0.42, again, from copying from previous page. Okay, omega max 39 radian per second. T I'm computing using that formula, which I showed before, which will be some 0.04 approximately. Okay, and K I computed also before, it's 1440. Remember, all right? That's it. Basically, I designed the controller, which would be 1440 times all of these numbers putting into that formula and getting my controller. Step response and closed loop will look like that. And if you put in, again, right click and characteristics of the transfer function and closed loop, it will give you overshoot of 22. Okay, 22.6%. And you wanted 20, which means it's not satisfying the original requirements of the design. It's not far, it's close, but it's not perfect. Which means that if you are required really 20% and not 22, you cannot leave this 22% for whatever reason. So you think your grade will go down or whatever, pointing to you, yes. Typically that's okay, like 20 and 22%, it's not a big deal, really. I mean, nobody will even notice in physical practice because you have so many approximations here. And it's all more or less theoretical, and you will never have an exact transfer function, ever. So 22 is fine. But if you want to make it even lower, you need to play more with the parameters to move a little bit here and there until you get overshoots that you want. All right. And as you can see, peak time is close to whatever you wanted. You wanted 0.1. Now it's 0.07. So peak time is satisfied. It's one of the requirements. You got it right. Now, also bandwidth should be fine. So if you're looking at that point, it gets you to the 3 dB. Here will be much farther than something that you wanted. You want number already? What's the number? I wanted 46. Okay, it's broad enough. Okay, so it passes all of the frequencies. Okay, questions on the exercise? Yes.
Where does 2.38?
2.38, it's coming from
1 over B.
1 over V, yes. 1 over V, yes. Okay. Any other questions? Okay, so practically this is summarizing everything you need to know from the textbook. And now, next part, we have still some time. I want to talk about some simplifications on the entire theory of control systems. When I learned that kind of theory and all these equations, I was surprised to see that people are actually doing it because it was like too difficult, too complicated. Yes, like kind of art more than science, okay? Like play with the numbers, get to that plot and that plot, try to shift it a little bit here, try to shift it a little bit there. Not great. And I asked myself simple questions like, can we do that simpler? Like, I cannot believe that control engineers are actually sitting and doing that. They're not, okay? Disclaimer. Nobody is actually doing that. Not that way. So this is theoretical for you to understand some reasoning behind what people are actually doing, okay? But nobody in practice using any of that type of designs, okay? And classical controls are pretty old theory. After that, you have many more theories in controls, like order control, loss control, nonlinear control, output control, and so on and so on. There are theories how to do that in computer much easier without going through all these procedures, okay? But I asked much easier questions first when I learned that kind of topic. My understanding was that the goal of control system is to close some loop, to have some reference signal, like where I want my output to be, and to achieve that output using some controller, introducing some sort of modification to input signals of the plant. You have plant, you have some disturbances, inputs, noises, whatever, but you have reference, and this is what you C want to be. Which means you want to have C equals to R. And frankly, I hate that notation in the textbook, only Y, C. Like output needs to be Y, not C. I don't know why they call it C. C is controller. Whatever. So the output needs to be as simple and as close as possible to R. This is the goal of any control system, right? You're designing controller, G of C, such that the signals will be such that C will be equal to R as much as possible. They will never be exactly, but that's what you want. Any objections to that kind of idea of control systems in general? That's what you want, right? You want it to be stable. We want it to be like output equals to input or reference. You don't want to invest a lot of control effort, which is that U signal called control effort. You don't want to spend any energy, ideally no energy at all. Again, can you achieve that? All right, so here's the idea. I'm taking that wire from here, connecting it there, between these 2 points. This is my new controller. So practically speaking, R is connected here. So R minus R will be 0. So error will be always 0. 0 multiplied by whatever controller, who cares? Nothing. Okay. The output C, since I disconnected that thing, will be equal to R because I'm connecting that directly, right? So is it ideal controller design? What's wrong with it?
There's no output.
There is output. Here you go.
There's no point to the whole system because you're just taking your input to the output.
Right? So isn't that what you want?
What's the point of all the other blocks then?
Does it have to have any meaning or reason to be there? Use controllers, just connect them directly to all. That's it, you got voltage that you want. If you have input voltage that you want to get as the output, connect it to the output and done with it. What's wrong with that?
It works till it doesn't.
Makes sense.
We use the system.
Why?
It's a function.
We're speaking in generalities. It's hard to define, like if I have a blower system and I want to control the amperage of the blower that I'm feeding into it based on the pressure on both sides, like
You're getting close. Yes. Yes.
So the idea is that in order to get an output close enough to the input, you would have to constantly adjust towards that. And when you take,
You know what? Why? I don't need to adjust here anything. I'm connecting it directly. So if my input voltage is like sinusoidal wave or step function or whatever it is, it will be reflected in the output directly. So I will measure exactly the same thing, which I wanted in the first place.
Want to eliminate the noise.
No noise. I mean, my input noiseless. And obviously you have some noise, but you can ignore it. It's like tiny noise in the input, yes.
This is somewhat related, kind of off topic. Let's say you have many outputs and you only have one input. You know the outputs that you want. How would you know the best input for your system to put in? I know it depends on all the,
Yes, this is a difficult question in a sense, but all control systems, you start that you have the answer first, right? You have reference, so you know what you want. If you don't know what you want, this is difficult to answer really what you want. It depends on the system. for any system, but yeah, this is a separate question, it's a separate problem. Like, how do you know what reference you want in the first place? But assuming that you know what you want as the output, and I give it to you that generator, that signal, whatever it is, okay, reference signal. Maybe this is a step. I'm putting that as my output. What's wrong with it?
There isn't anything wrong with that right there.
It's a lot wrong with it. First of all, what I said at the beginning was wrong. Okay? The goal of control systems is not to generate output, which is following the reference. Okay? Not at all. The goal of control system to control, as name states, okay, to control particular plant to produce output which you will measure, and that output will follow the reference signal. Okay, big difference. Let's say you have motor, okay, and you want that motor to rotate 300 rotations per minute. Okay, constant angular velocity. All right. I can put voltage of 300 millivolts or milliamp or whatever to the output, motor will not rotate, okay? Cares. I don't care about output which will be equal to input. It's not the point. The point is that I want to rotate the motor with that speed and not to have output measured, which is 300 number, whatever it is, okay? I want the effect on plant to be such that the output will follow the reference, right? So this is completely different goal. It's not that output equals to input. No, the effect, application of voltages or whatever other forces on plant need to be such that the output will follow the input. Very different goal, all right? So this is clearly nonsense. It's not doing anything. The motor will not rotate at all. Your goal is not satisfied really, all right? Okay. How about that kind of simple design? So my controller is 1 divided by plant transfer function, 1 divided by G, which gives me overall transfer function of what?
RT.
1. Okay, which means that C equals to R again. What's wrong with that? Great design, right? Saying, oh, is that design?
Really controlling anything.
Same.
There's no transfer.
You mean it's not transfer? Now I'm controlling G with just one inverse dynamics. Yes.
There's no feedback loop.
Also what?
There's no anything. It's R is equal to C.
R is equal. Sorry?
R is equal to C.
Yes, R is equal to C. That's what you want, right?
Oh.
Why not?
It's
Yeah, in that case, you are measuring output of system G, which is like motor is already rotating, doing whatever you're measuring, and C equals to R.
We're not controlling anything,
Is it?
just an input.
Of course, you control it. You control it. You're sending input signal U, which is control effort, by that controller from your reference input, such that your C will try to mimic whatever R is doing because this is inverse dynamics of G of S. I inverted the dynamics, pulling it through, get to the second one. Motor is rotating, measuring C. So now I have control. It's open loop control, yes, but still I have some.
Where are you measuring C? You have no measurement of C.
I have tachometer.
know what it
No, I have measurement. I mean, at the end, I have here tachometer, which is measuring number of rotations per minute, whatever gives me some number. This is my output.
part of the system, basically doing nothing.
No, it is doing everything it needs to do. What do you mean it is doing nothing? I'm computing output signal here using the transfer function. Okay, computing that input here. I'm putting that voltage into the motor. It starts to rotate, obviously. What's wrong with that? Yes.
What is the difference between this system and the system in the last slide?
So in the last slide, the motor got zero input. There was no input. This is like 0 here, 0 here, 0 here, 0 here. Nothing coming to the plant at all. And I'm not even measuring the output of the plant. That one, I'm measuring the output of the plant, which is the actual number of rotations per minute. And I'm giving it some input, which is whatever that function produces as a function of, let's say, step response. Okay, so giving step response here, computes the output voltage, whatever it is, gives it to the motor. Motor starts to rotate somehow. My claim is that since these two transfer functions are equivalent to transfer function of 1 from R to C, I get them equal.
One, your output is same.
I do want the output to track the input. This is what goal of the output of the plant needs to track the reference. This is goal of control systems.
Would this be like your RTU to your SCADA? Like if you had a panel that was your remote terminal unit and then C would be your SCADA. You're just transferring the data.
Not really. Okay, so here we have a lot of different issues with that approach. A lot. First of all, nothing is wrong about the controller in general. Okay. People are doing inverse dynamics controllers in open loop. And it works. So, not great. That's one of the simplest controllers, really. 1 divided by G. But it has lots of different issues, typically. Okay. So here are the issues. First of all, typically you don't know parameters of G exactly. So the coefficients that you have in function G are approximated from some sort of estimation process. Okay. If you have approximation, you don't know what G is. It's uncertain. All these parameters could be in some range or could be a little bit different or could even change with time. So if your controller is 1 divided by G, you don't know what the G is. It will be another approximation of one of the possible transfer functions G. And you're not controlling for errors, which means you don't know how far away your controller is from inverse of the G, of the actual G. Okay, and actual G might also change in time, so you have no idea how. Okay, because you don't have any feedback, so you have no control over it. They might be pretty different. Okay, so you'll generate incorrect signal. Might be close if you're lucky, but you might not be lucky. Okay, you don't want to build on luck when you're designing control systems. Disturbances, which are coming typically somewhere in the middle, noises, other things will not be taken into account at all. So you will not have any response to any kind of disturbances of noises. They will propagate directly through all of the system, and you will see them as the output errors. Right? Again, because you don't have any feedback loop. Don't close in your feedback loop, you cannot control for it. Transfer functions. If you remember from 318 course, signals and systems course, transfer functions do not have any initial conditions. They by definition have initial conditions 0. But real systems do have initial conditions, okay? You do not take them into account. You're just ignoring all of the transient response at the beginning, where you have some response to initial conditions plus response to input, okay? So you completely ignore that part. So your 1 divided by G will start with completely different initial point, okay? And they might not even converge to each other, actually, because you have open loop and you don't have any way to control where that system is right now, at what state it is right now, okay? What voltages, maybe it already was rotating at the beginning. Who told you that it was at 0 angle and 0 speed when you started to give your step response, okay? Maybe it was already rotating from previous stimulus or whatever. Right? You don't know. And you don't have any feedback loop to correct it. Right? And this is really big one. Okay. You remember what proper system is? Strictly proper system. Strictly proper system is when number of zeros is less than number of poles, and proper is when they are equal. What happens if you have more zeros than poles?
Unstable system.
No, it still might be stable. It's not causal system. Means in practice, you cannot even implement that system where you have more zeros than poles. you need to know future values of your output to implement that system, okay? To compute it from input. It's not causal. You cannot implement it in practice. So you can only approximate it somehow with adding additional poles here and there. It will be kind of pretty fast to the left, but it will be only approximation of 1 divided by g. You cannot implement physics 1 divided by g. It's not proper system because typically you have more poles than zeros in g. When you're inverting it, you have more zeros than poles. Not good, right? Not implemented physically. Any system which needs to look into the future to compute its present. Not look in the future. Any questions on that? Shocking? Not too much? Okay, I'll try even something even more shocking, okay? All right, let's say additional simple design. Instead of going through all of these headaches of Bode diagrams or locuses, I know that all of the poles on the left give me good performance, good characteristics, everything I want from the system. So if my closed loop system will have all of the poles where I want them to be, I'm good in terms of design, okay? I designed good system. This is what you did in root locus multiple times, but you played with all these values. Forget about all these values, just decide where you want them to be. When you know where you want them to be, zeros and poles in closed loop, you can write closed loop transfer function should be stable, all the characteristics wherever you want them to be, beautiful T of S. This is closed loop transfer function, okay? Now, you have unknown controller, which we will call G of C, GC controller, and open loop transfer function G. So you know the transfer function in closed loop equals ZG times ZG divided by 1 plus the multiplication again. Remember that formula?
Yeah.
Unit feedback. Even controller, plant, unit feedback. This is a formula to compute transfer function in closed loop. And I know that transfer function. So this is one polynomial divided by another polynomial of some kind, right? I also know that polynomial divided by another polynomial, numerator and denominator, right? So G of S is also defined. This is our plant. So do some algebra of that equation and compute what is G of C. And this is what you will get. Like basic algebra, middle school algebra, okay? Think about this is some value, this is some value, this is some value, and so on. Like, compute it backwards. You know, you just multiply both sides by that same, then you regroup the G separately in parentheses, divide one by another, and you get that one as a function of desired closed loop transfer function. And your plant done by design. What's wrong with that? Why do we need all of that textbook of 1,000 pages telling us how to design stuff? I'm done. Like this is Control Systems 1 course done. What's wrong with that?
It's nebulous.
Design it the way you want it, like where you want your poles to be, where you want your zeros to be, and you're free to choose them anywhere you want practically on the left semi-plane. Farther to the left will mean that they will become faster, but like bandwidth will be too, like farther from the axis will give you higher overshoot, closer to the axis will give you lower overshoot. You have all kinds of things that you can play with, but practically just design where you want the poles to be in closed loop, put them in that formula, done. What's wrong with that? G of S is known. G of C, you compute G of C using that formula. This is your controller, right? G of C, you want to compute controller. So your controller will be just using that formula. Done.
But G of C is unknown.
T of S.
G of C. GC is
You're talking about this one?
Yeah.
You compute it. This is what G of C is. I define it that way. I define my controller to be that thing.
Do we know what T of S is?
T of S, you choose whatever you want. Just stable somewhere in the left semi-plane.
It doesn't have disturbances.
It's closed loop, you will not have any problems with disturbances.
Design doesn't finish when you get all your parameters together. You have to test your design.
I mean, you can test it. I mean, here is testing of the design. Closed loop transfer function will be that same. When you design G of C to be using that formula, T of S will be that same, right? So it will be closed loop. And it will be your desired transfer function in closed loop, right? Because you, in the first place, designed it to be that. So obviously it satisfies all of the design criteria because you designed it in the first place, right? You started with it. It will have all of the characteristics that you love to see your system in closed loop. Designed it that way. Just thrown on me that function in closed loop. Yes.
You said GFC is unknown, then how do you know about TFS? Because GFC.
The T of S might be like 1 divided by S plus 1. Okay, how about that? 1 divided by S plus 10. Depends on how fast you want your system to be.
Then you will know GFC.
Then you will put the T of S here and you will compute G of C. Yes.
So. But you originally say GFC is unknown, but now you say you can compute it.
Right, so I'm saying my design procedure is super simple. I just choose T of S. That will be like fast, great, and closed loop. I choose just closed loop transfer functions that I would love to see, okay? So I just choose whatever I want to see, okay? Wishful thinking. I choose whatever I want to see as closed loop transfer function, and I will call it T. Then I put that T into that formula, and I compute G of C. What's wrong with that? And it's promised that my closed loop transfer function will be that T of S.
Does it cause a non-proper system again?
No. Why would it? Not necessarily, no.
There is nothing wrong.
There's nothing wrong with it. Except one thing. Practically all controller designs are that way, okay? Like any single possible, like pick root locus designs, pick any design, okay? Any answers that you will receive using Bode, whatever, they all will follow that formula. You will have TS such that it satisfies that formula and your controller will be computed using that formula for any possible design in general, all right? There is only one little thing with that. Okay. Here is that little thing. Let's say your transfer function G of S is 1 divided by S minus 2. Something simple, okay? You have single pole, no zeros, and you want your transfer function in closed loop to be 1 divided by S plus 1. Nicer, right? Stable. Settling time is 3 divided by sigma, which is 3 seconds, approximately 9 seconds, whatever. You like it, okay? You can choose something else, it doesn't matter really. Something stable. So I'm putting numbers into that formula, and this is what I get, G of C. So what's wrong with that part? S minus 2 cancels, and I get 1 divided by S. That's it. Then I multiply GS by G of C. So it's 1 divided by S divided by 1 plus 1 divided by S. I get 1 divided by S plus 1. That's correct.
Unstable.
Right. Remember? So practically G, C, G equals. So you have G is 1 divided S minus 2. Then multiplying it by S minus 2 divided by S. All right, so this cancels. You get 1 divided by S. All right. So GCG divided by 1 plus GCG, which is T, all right, equals 1 divided by S divided by 1 plus 1 divided by S plus 1 divided by S plus 1, which is what you want in closed loop. Correct?
The controller is
Is this good
unstable.
design or bad design? This is the question. I'm proposing controller which is that it's proper function, right? No problems with that. You can implement it as minus 2 divided by s. It's proper function. It's actually 1 minus 2 divided by s with my controller. It's constant plus integrator. It's PI controller. Have you heard about PI controllers? So it's PI controller, which is 1 minus 2 divided by s. PI controller. What's wrong with it?
Like what we said earlier, consider a proper system, or is it the same number of?
No, it's proper system. S minus 2 divided by s is proper. Have same number of zeros and poles. But it should not have more zeros than poles, then it's not proper. But if it is equal, it's okay. It should be equal or smaller number of zeros. Be implementable. But this is regular PI controller, so it's definitely implementable. What's wrong with the controller?
Is it outside our gain margin, which
Having a 0 in the right-hand plane cause a problem.
What problem?
will be unstable?
So 0 is not causing instability. So 0 is causing typically undershoot, but many systems can live with undershoot, which means you cannot get rid of that. If you have step response instead of that step response, you will have that kind of step response, which is undershoot and then going up to converge. Well, this is kind of not real issue for most systems, especially if it is not huge. So look at practical perspective on that system. Again, you don't know G of S precisely. What will happen if instead of 2, I'm putting here 2.000000001, which is practically the same thing. Instead of that, I have practically same transfer function, right? But this will not cancel with that. Right? If it will not cancel with that, and you compute the overall closed loop transfer function, it will not even be stable. Or not even close. It will be very unstable. You cannot cancel unstable zeros and poles at all. Which means that yes, this design is completely fine if you know how to choose the function t. Okay, and choosing function t is not super easy, really. This is a problem. So some transfer functions t might work completely fine, and you will have pure designs, everything will be fine with your choices of t. Some others might cause a lot of trouble, and you will have a lot of cancellations of that kind, and you don't want to cause that type of problems. So for positive systems, then this will be plus. It's not really a big deal. It's not a problem. In most cases, it will work fine. If original system is unstable, then you'll have tons of trouble designing that way. All right, you need to be extremely careful designing that way, even if you are using just regular PI controller, even with root locus. You don't want to cancel anything on the right side. Approximately. Okay, you don't want even to come close to canceling anything on the right side, not zeros and not poles. Okay, don't touch the right side. It's dangerous. This is the point. Any questions? Yes.
So is there a technique in control systems where you can have a controller that completely cancels anything that you could have on the right side?
Simple answer is no. Okay. You have cases where you can do particular things which could. You do have techniques, not in linear controls, and not for zero and poles directly. So the answer is no, probably.
Accurately, so GCOG could be.
Yeah, so typically that kind of design will cancel the different kind of things and you don't want to cancel them because they will not be canceled precisely and cause all kind of troubles.